Okay, cool. So yeah, thank you for the invitation. Glad I can be a small part of the bootcamp this year. So my talk will give a very brief introduction to adversarial examples in deep neural networks. I think it's a very interesting topic, and it's a very big research field. Um, and it also tells us a bit about how neural networks work. So I hope you find it interesting. So I'll just jump right into it then. Okay, so I'll start with what is an adversarial example. So imagine you have a picture of a whale, and you show this picture to your friendly neighborhood neural network, and it classifies it as a whale correctly with a rather high confidence. It's 90% sure it's a whale. This is all good and normal. However, what we can do is we can add some targeted noise to this image. Now the image essentially to us humans looks exactly the same. If you show this to anybody, they would still say that's a whale. Nothing really has changed in the image, nothing meaningful anyway. However, if we now show this image to that same neural network, it will predict this to be a panda with very high confidence as well. So the network is confidently incorrect. Now, these examples that to us humans are clearly one class, but is misclassified with a high confidence by neural networks, these are known as adversarial examples. Now, you can imagine that they are a very big issue in the deep learning field. If you're building an autonomous car, you can imagine that if it doesn't recognize a stop sign due to some sort of noise, you can have life-threatening consequences. Similarly, in the medical field, which is what I'm working on at the moment, you can also find these adversarial examples. So here we have an example of a normal chest CT. We can add some carefully calculated noise to that again, and now the network thinks that this patient has lung cancer. So adversarial examples are a big problem, but they're also very interesting because they betray something about how neural networks perceive the world, and that's why I want to talk about today. It's also worth mentioning that adversarial examples are not just limited to images. Nowadays, you can also do them language. So say you have a chat assistant, something like ChatGPT. If you tell it, hey, tell me how to build a bomb, normally it will refuse. It's been trained to not provide any harmful, potentially harmful information, and it should say, I'm sorry, I can't do that. Can you add something else? However, if you ask that again, but add a bunch of carefully crafted exclamation marks, which something that's known as an adversarial suffix, then the assistant obliges and says, sure, here's how to build a bomb, and gives you a bunch of examples. Okay, so to really understand adversarial examples, first we need to talk about how they are created, how they come to be. Now, how we do this is we use something called an adversarial attack algorithm, some algorithm that's attacking a neural network, and then you get an adversarial example out, something that fools the neural network. Now, there are a bunch of different ways of doing this. There's a bunch of different adversarial attacks, but they all work on essentially the same underlying principle. So to explain that, let's consider an example. Let's say that I have a image classification problem. I'm trying to distinguish between pictures of dogs and cats. And now let's say we take a two-dimensional projection of this data set, and it might look something like this. All of the blue dots here are dog images, and all of the red dots here are cat images. Now, when you train a neural network on this data to classify cats and dogs, what it's actually going to be doing at the end of the day, it's going to be learning weights such that it can separate these two classes, such that it can separate the training data of cats and the training data of dogs. So in this case, it's going to learn what we call a decision boundary, essentially some separating hyperplane that separates your two classes. So everything to the right of the decision boundary, So in this direction will be classified as a cat, and everything to the left will be classified as a dog. On the decision boundary, that's just where the neural network will be unsure. It will give equal probability for the dog and cat class. It will be 50-50. So to craft an adversarial example, say from this cat image here, this red dot over here, all we need to do is we need to find the minimum perturbation that we can add to this image that will put it to the other side of the decision boundary, that will move it to this left side. So essentially the minimum perturbation we can add to the example such that the network will misclassify it. And the size of this minimum perturbation, the distance you need to move the sample, is known as the margin. Now, unfortunately, it's very difficult to actually find this minimum perturbation. There's no analytical solution to this, so we have to use numerical methods. So I'll just talk about one of those very briefly. It's fine if you don't fully understand the method. It's a adversarial attack known as projected gradient descent, and that's why I'm showing in this right-hand graph over here. So how it works is we take one of our samples, say this one, and then we put it here in the middle. So this X here is our sample. And then we define some small ball on the sample. I'll come back to this ball in a moment. What we're visualizing here is the loss landscape for this neural network in the region of the sample. So this is in the input space. So essentially, just what this is showing is that this sample is labeled as a cat. And if you compute the loss between your network's prediction for the sample and the label of cat, you can see how the loss will change. So if we move the sample slightly, add a little bit of noise, say in this direction, its loss is going to be higher. If we move in this direction, the loss is also going to be higher. So all that projected gradient descent does is it tries to find the point in this ball that maximizes the loss. And usually it turns out that the point that maximizes the loss, which in this case would be this point over here, usually this point is actually on the other side of the decision boundary. So this point over here might correspond to, say, a point over there, just on the other side of the decision boundary. So we just use gradient descent essentially to find the point of maximum loss instead of trying to find the point of minimum loss like we normally do when we're training a neural network. Now, the reason for the ball is we want to control the size of our perturbation. If we just try and find the point of maximum loss without this ball, we're going to find a point very far away from the sample, and it's not going to look like a cat anymore. If you perturb it enough, your cat will start to look like a dog. So we make this ball very small. We say in a very tiny area around this cat, can we find a point of high loss? And that's how you can craft an adversarial example. So the point over here would correspond to an adversarial example, a cat that still looks like a cat to us, but the network will classify it as a dog. So as you can imagine, there's been a lot of work done to make neural networks robust to these sort of attacks. So these are known as adversarial defense methods. So we don't want our networks to be so easily fooled. We don't want them to be susceptible to these attacks. So we try and make them robust to these adversarial examples. Now, there are many ways of doing this. There's been about a decade, or actually 11 years now, of research into this topic. And there's a whole class of methods. The two most popular ones that I'd like to highlight is one known as adversarial training, which is quite simple. It's sort of like a kind of data augmentation. So all that you do is you perturb your training samples as the network's training. You actually craft adversarial examples. So that teaches the network to be robust to these attacks when you're testing it. So for each cat that comes in, you slightly perturb it so that the network thinks it's a dog, and then you tell it, hey, don't classify this as a dog, keep classifying it as a cat. And this way you can kind of build invariance to this sort of adversarial noise into your network. The second class of methods is what I call margin maximization. you remember the margins I mentioned earlier, the minimum distance you need to move the sample. In margin maximization methods, we just want to encourage our network to have large margins. So here again, I've got a simple 2D data set, and this is the separating decision boundary. And you can see that these two examples have very small margins. We want to encourage our network to have large margins, so we rather want to learn something like this. In practice, how we do this, it's really quite simple. So we just adjust our loss function. So you should know, I think, from the practicals that when you're doing a classification problem, we often use the cross entropy loss function. So it'll be the cross entropy between your label y and your model's prediction y hat. But now with margin maximization, we just add an additional term to that. We add this margin maximization loss that's weighted by this constant lambda here. And all that this margin maximization loss does is it's high if the model's margins are small. So in this way, it encourages the model to learn larger margins. And if those margins are larger, that means that you have to use larger perturbations to fool it. And so it's more robust to adversarial attacks. And that is the core idea. Okay. So you might be wondering now, do these defenses work? Well, the answer is a bit complicated. It boils down to kind of. So what I'm showing here on the right-hand side is a screenshot from something called robustbench. Robustbench is a standardized benchmark in the robustness field that tries to systematically track the progress that we're making towards building adversarially robust models. And how it works is that it's centered around the CFAR10 dataset, which you should be familiar by now, a simple 10-class classification problem. And you should know that nowadays we can easily build models that get 99% test accuracy on the CFAR10 dataset. So how this robustbench works is you submit a model, and then adversarial examples are crafted from the CFAR10 test set. These are then shown to your model, and you just record how many of them it still classifies correctly. So you get what we call a robust accuracy. And you can see that the state of the art at the moment is around 73.71%. So clearly, if we know that on the normal test set we can get around 99% accuracy, there's a big gap between what we can do on normal images and what we can do on adversarially attacked images. Now, to make matters worse, how we got to the 73.71% is actually also not satisfactory at all. So one of the big issues with doing something like adversarial training, or even for margin maximization methods, is something known as robust overfitting. So I want to direct your attention to the graph here on the left side. What I'm showing here on the x-axis is training steps, and on the y-axis it's accuracy. And this is just training curves as a model trained on CFAR10, adversarially trained on CFAR10 is learning. So this blue line here is showing the model's accuracy on adversarial examples of its training data. So that's what it's being trained on. And you can see that as the model learns, this accuracy increases steadily, and it gets almost 100% accuracy on these adversarial examples on its training data. However, if we look at the orange curve on the test set, we see that the performance quickly plateaus around just above 40% accuracy, and it doesn't improve any further. So essentially, the model is overfitting to attacks on its training data, and it's not learning to generalize those the robustness it's learned to unseen examples, to the test set. So one way of mitigating this phenomenon of robust overfitting, people have figured out, well, we could just throw more data at the problem. So what people do is they generate more CFAR10 images. So they use things like GANs or diffusion models that Prof. Marley mentioned in the previous talk, and they just generate more training data. And if you train your model with more training data, then we can make it more robust. So if I zoom in on the top solution here, you'll see that there's a little note that says it uses an additional 300 million synthetic images in training. So I want you just to take a moment and consider how kind of silly this is. This is a simple 10-class classification problem. We can easily train with a single GPU, we can train a model that's 99% accurate on standard data on this data set. But to get it to have only 73.71% robust accuracy, we have to use, well, firstly, generate 300 million synthetic images and then train on 300 million synthetic images. You need a truckload of GPUs, of graphics cards, to get this simple performance on a simple 10-class classification problem. So clearly, this is a problem that's not nearly solved, and there's still a lot of work that needs to be done, even after 10 years of research. I actually want to highlight how bad this problem is. So this is a graph from the paper that currently holds the #1 spot on the leaderboard. And what they're showing here on the x-axis is training flops, or training floating point operations. And you'll see that it's logarithmic scale. On the y-axis, it's the adversarial CIFAR-10 test accuracy. What they did is, I want you to look at the green line here. They looked at all of the other submissions on the leaderboard, including their own, which is the star over here. And they looked at how much floating point operations, essentially how much compute was needed to get to that test accuracy. They then fitted a curve to this. And now we can roughly predict how will the adversarial test accuracy look if we have more compute, if we have more floating point operations. And you can see that at the moment we're sitting there at 73%. And if we were, say, want to get to 80%, you can see we'd need around GPT-4 level of compute. So that is entire warehouses full of graphics cards training away, probably for a month or so, being powered by its own nuclear reactor because it uses so much power, just to build an 80% robust CIFAR-10 classifier, which of course is just ludicrous. So yeah, clearly this is a very difficult problem, and just scaling data and scaling our models is not going to solve it in an effective manner. Some other interesting things on this graph I could maybe quickly point out is the other lines, they're just showing what would happen if you use different quality of generated samples. So what this is measuring is something called Frechet inception distance. It just measures how well your generated examples match your original distribution. So how realistic are your generated images in this case? And you can see that if we use poorer generative models, then this curve looks a bit worse. And if we have a hypothetical perfect generative model, then it looks a bit better. Also quite interesting is in this paper, they actually found that the human limit is not 100%, it's 90%. For CIFAR-10, since the images are so low resolution, even though we only add very tiny perturbation to the images during this, when we're creating adversarial examples, there are sometimes, around 10% of the cases, where even such a small perturbation does actually change the meaning of the image. So here they're showing a horse, and if you add a very small perturbation to it, it does actually look like a dog. You can see that this looks a lot more dog-like than it does horse-like. So the human limit is around 90% CIFAR-10 test accuracy. Okay, so this is a very difficult problem. You might be wondering, why do these adversarial examples exist at all? Why are neural networks susceptible to these kind of attacks? Us humans aren't susceptible to it. What's going on in kind of the visual perception of neural networks? Now, this question is still an open one. It's an entire subfield, actually, in the adversarial robustness literature, and there have been many papers written on the topic. One thing everyone seems to have found consensus on, though, in the literature, is that we figured out that it seems that one of the reasons why networks are susceptible to these adversarial attacks is that they tend to use sort of two different sorts of features. So say we have an image of a frog. We found that neural networks, to classify this image as a frog, to make predictions, neural networks use what we call robust features, and that would be the sort of features that us humans use. It might be something like the the color, the texture of the skin, the beadiness of the eyes, etc. But we've also found that they use something that we call non-robust features. These are kind of non-interpretable patterns in the images. They look like noise to us humans. I mean, there's nothing frog-like in this image, in my opinion. But the neural network has found that these noise-like patterns tend to be very predictive. They're very useful to actually classify things with. The problem is, one is that they're uninterpretable to us, and two, that they are very brittle. These patterns are very brittle. If you slightly perturb them, add a little bit of noise, then it's easy to flip these non-robust features from, say, the frog class to the cat class or something else. So we know that neural networks are susceptible to adversarial attacks in part because they rely on these non-robust features. So this is actually, in a way, a bit of good news, because if that means that if we train our models to be adversarially robust, those robust models actually have a few nice properties as well. One of them being that they tend to be a lot more interpretable. So I don't know if this has been discussed in the bootcamp yet, but neural networks are generally very, very difficult to interpret. This is from a paper in 2019. What they did is they trained a neural network on MNIST and CIFAR10 and ImageNet. And then they looked at they visualized the gradients of the loss function with respect to the input features. So that gives you an idea of what the neural network is looking at to make predictions. And you'll see that for a model that's just trained in the normal standard fashion, these gradients look like noise. They're not very interpretable. However, if you adversarially train this model such that it no longer relies on non-robust features, these gradients are actually a lot more interpretable. They're a lot more aligned with the human visual or human ideas of visual perception. So yeah, in summary, robust models tend to be more interpretable. Another cool thing you can do with robust models are generate what's known as counterfactuals. So a counterfactual is an interpretability technique that essentially just asks, what is the minimum change I need to make to this image before my model will classify it as something else? Now, of course, for a non-robust model, that's the exact same thing as generating an adversarial example. What's the minimum perturbation such that the model misclassifies the input? So you'll just, if you generate a counterfactual for a normal model, you'll just have the whale and the panda example again. However, if you have a robust model, then you can start to do some very cool things. You can have a picture of Isaac Newton and ask the network, how should this change before you think it's Albert Einstein? And you can see that the change is actually visually meaningful. Similarly, you can ask when would you classify this as Queen Elizabeth? And you can see how the image changes. Same for Nikola Tesla here. So yeah, this is where I want to stop. So just in summary, neural networks can be easily fooled. This is probably in part due to their reliance on what we call non-robust features, uninterpretable and predictive, but also brittle features that they learn to use. It's very difficult and expensive to make them robust at the moment. Even after 10 years of research, we still haven't solved this problem. And robust models have some nice properties. Take-home message here is just that all our networks are broken.